Here's a question for you. We haven't set foot on Jupiter, Saturn, Uranus, or Neptune, or any celestial body billions of light years away from us. So despite that, how do we know, for example, that the atmospheres of the planets I mentioned contain hydrogen and helium, or that Jupiter and Saturn contain liquid metal? Where do we get this information? I mean, we haven't gone there to see for ourselves. How can we know these things? All this information about the universe and what's happening around us. Where do we get it? There's actually just one answer to all of this, the source of all knowledge. Light. Yes, we've mentioned this countless times before, especially when discussing the origins of quantum mechanics and delving into electromagnetism. But what is light really? How does it form? We haven't discussed these yet. You can also think of this video as a fresh start on quantum physics. It's like a resource where you can find all the information needed to ground everything in fundamentals and continue our journey through the quantum adventure with greater preparedness. You know, so far science. I want everything to be clear. Let me give a quick heads up before we start. This will be a very information-packed video. At times, you might want to pause the video and take notes. We'll be discussing quantum physics, spectroscopy, the Doppler effect. We'll gather information from various fields and bring it all together at the end. So, as you know, after centuries of experiments, debates, and research, our final conclusion was that light is a wave. With Maxwell's contributions, we had found the answer to the question of what light is. Light is an electromagnetic wave. That's not wrong either. Let's start by examining this definition. When we say light is a wave, what exactly are we referring to? Yes, light is energy, and as an electromagnetic wave, it moves in waves, just like waves in the ocean. But what causes these waves in light is the electric and magnetic fields. Light is the intertwined state of these two fields. That's why another name for light is electromagnetic radiation. But let's visualize it in our minds. For example, since we mentioned ocean waves, imagine you're floating among these waves. A wave comes and you rise. Then another wave. You go up and down. We call the region between these two waves the wavelength. It's a term frequently used when discussing light, wavelength. And the most important characteristic of light is this wavelength, because the energy of light depends on the length of this wavelength. For example, light with a shorter wavelength has higher energy, while light with a longer wavelength has lower energy. We can observe this energy at any moment, thanks to colors. For instance, when you say you see something purple, we're actually talking about light with a short wavelength reaching your eyes. Red has a longer wavelength, so we can easily say that red has lower energy than purple. All the other colors we can see also have their own wavelengths, and this range of different wavelengths that colors possess is what we call the spectrum. However, the colors we can see are just a very narrow part of an enormous spectrum. This is because our eyes can only perceive the strongest light emitted by the sun. That's how we see things. If a light's wavelength is slightly shorter than what we can see, we call it ultraviolet. If it's even shorter than that, it's X-rays. Gamma rays have the shortest wavelength we know of. Or if a light's wavelength is slightly longer than what we can see, we call it infrared. If it's even longer than that, we call it microwave. We call the light with the longest wavelength a radio wave. By the way, these wavelengths aren't clearly separated, but when we consider them all together, we call the entire spectrum the electromagnetic spectrum. And we've also mentioned that wavelength is inversely proportional to energy. So from this perspective, the rays with the highest energy are gamma rays. The ones with the lowest energy are radio waves. Now, if we step back and look at the entire spectrum, you'll see that the light we can see is very, very limited. We didn't just sit idly by regarding the parts we can't see. We developed countless telescopes. They opened the door to worlds we couldn't see. But there's still a question here. Where does this light come from? What is its source? Where does it come from? At this point, we need to briefly discuss matter. We've touched on this before. One of the most fundamental properties of matter is this. When you heat matter, its energy increases, and matter is not content with this highly excited state. It will do anything to return to its original state, its standard energy level. And we know that light is a form of energy, so it releases the excess energy as light, and in doing so, naturally emits light. But how do they emit different types of light? What determines this? Here, another property of matter comes into play. The light emitted by a hot object has high energy. In other words, as you know, the wavelength is short. The light emitted by colder objects, on the other hand, has lower energy. For example, you can observe this when you heat an iron rod. It first glows red, then orange. As it heats up, it turns yellow. As it heats up, both the wavelength and the color change. Ultimately, it emits light that turns blue. As the energy increases, it becomes bluer. As you can see, astronomers' perception is a bit different from ours. We generally associate cold with blue and heat with red. But science doesn't care about such perceptions. Red is cooler than blue. Besides, when we turn our gaze towards the vastness of space, we also see structures with extremely low light-emitting density. Gas clouds, for example. To understand this, we'd actually have to go examine these clouds, examine their atoms under a microscope. But we don't need to. Why? Let's dive back into the quantum world for a moment. Because to understand this topic, we need to take a look at this extraordinary universe. Let's talk about atoms. We know what an atom is made of: neutrons, protons, and electrons. Protons have a positive charge, electrons have a negative charge. As for the neutron, well, the name says it all. It's neutral. While neutrons and protons are found in the atom's nucleus, electrons, as you know, now whenever we say atom, the image that comes to mind is the electron orbiting the nucleus. But the exact location of the electron isn't really clear. Somewhere around it. Actually, it's everywhere at the same time. Anyway, we'll discuss this later. The point here is this. The electron has a very limited, precise, and specific location it can occupy around the nucleus. This depends on the electron's energy. The positions where an electron can be found are strictly defined by rigid rules. It's either one or the other. There's no in-between. Think of it like stair steps. An electron can be on the first step or the second. It can't be in between. So when you climb the stairs, you expend energy with every step. If you're very tired, meaning you have no energy, you stay on one step. The same applies to electrons. When given enough energy, they change their position instantly. Do you remember the quantum leap? But they constantly strive to return to where they started. To do this, they must release this energy. How do they release it? Yes, light. When you shine light on an atom, the electrons gain energy and undergo a leap. As they return to their original position, they release their energy in the form of photons. This is what produces light. By the way, it doesn't necessarily have to be one step. With enough energy, they can jump 2 or 3 steps at a time. But as we said, there's no in-between. That's exactly what Max Planck discovered. The fact that light behaves like a particle is based entirely on this. It's the starting point of quantum physics. Also, remember we said energy and wavelength are the same thing. Colors correspond to these as well. They're all essentially the same thing. So when an electron jumps up or down, it emits a very specific color depending on its position. This is precisely why each atom emits light in different colors. So how does this work? Let's proceed step by step. When we think of stairs, we picture steps of standard size, but it's not like that with atoms. Each step can be a different size. For example, when an electron and hydrogen atom jumps, it emits light of a very different color compared to electrons in helium or calcium atoms. And this is the very foundation of the universe. We can indeed determine what an object billions of light years away is made of in this way. Different atoms emit light of different colors, and by measuring this light, we can see what the object is made of without even going there to measure it without even going there, no matter how far away it is.
Isn't that amazing? But how do we do it? I mean, how do we measure light? Of course, spectroscopy. That is the study of how light interacts with matter. And there's a device called a spectrometer. Using this device, we can determine the exact wavelength of a color. You might be thinking of that famous dress right now. Is it blue or gold? Yes. When measured with a spectrometer, it was determined that the dress is both colors, so no one is wrong. Considering the biological aspect of color perception, factors like the camera used, ambient light, and angle, this is the result. Everyone is right. Both are correct. Anyway, we mentioned that using a spectrometer, we can see the wavelength of light. From this perspective, we can also understand the difference between the light emitted by a helium atom and a hydrogen atom. And when you attach this spectrometer to a telescope, you can guess. We can see what stars are made of, and that's how we learn about the universe. And going back to the original question, we know that stars and gas clouds are mostly made of hydrogen, a bit of helium, and some heavier elements. Jupiter's atmosphere contains methane. Venus has carbon dioxide. Everything in the universe has its own unique composition. With spectroscopy, we can analyze these. But that's not all. We can also determine how fast an object is moving, which way it's rotating, whether it has a magnetic field and how strong it is, as well as its mass and density. I'd like to briefly mention one more thing at this point, the Doppler effect. You know, that phenomenon where the sound reaches its peak as a motorcycle speeds right past us and then gradually fades away as it moves away. Sound has a wavelength, you know. At the peak, the wavelength is shortest. As it moves away, the wavelength gets longer and longer until it disappears. The same applies to light. If an object is coming toward you, its wavelength narrows and shortens as it approaches. We call this the blue shift. And as it moves away, the wavelength lengthens. This is what we call the red shift. When you apply this shift to the spectrum, you can determine whether an object is moving away or toward you. Why is this important then? Because this is how we learned. The universe is expanding. And now, shall we open a new door together? After reaching the present day on our journey through quantum physics, let's begin a new series. Let's talk about galaxies, stars, black holes, quarks, supernovae, and so much more. Let's embark on an exciting journey. I want to get lost in the gas clouds. What do you say? And as always, until we meet again, thank you for being here. Best wishes.